Hello, welcome to the fourth week of the course on audio signal processing for music applications. And in this demonstration class, I want to continue what we started in the last one, which was to analyze a sound, in that case, a sound of a soprano, using the short time Fourier transform, the topic of this week. So in this lecture, I want to analyze another sound, a sound that can give us another view of the short time Fourier transform. So let's open the Sonic visualizer, and this is the sound we're gonna analyze today, and this is the sound of a piano. And so let's listen that. Okay, so this is a very simple piano phrase, quite clear, 5 notes. So let's go directly to the SMS tools, and let's go to the short time Fourier transform module. So let's go to the piano sound. That is here, piano.wav. Okay, and now let's decide about the parameters. Okay, in the last class we mentioned that the Blackman was a quite good choice for what we were doing, so let's keep it. The window size, okay, this is not as a high pitch as the voice, so we will need quite a bigger window size. So I don't know, let's start with, for example, let's say 1501. This is an odd size window, and this is something that we will, whenever possible, we will do. If we take windows with an odd size, that means that they can be centered around 0, and especially for the phase analysis, that's going to be very convenient. So let's use that, and let's take that as a habit of using always odd size windows. The FFT has to be bigger than that, and of course normally now we will be always using power of 2, so that is efficient. You can use the FFT algorithm. So the power of 2 bigger than 1500 is 2048. Okay, that's a good size. And the hop size has to be, for the Blackman window, has to be a hop so that the windows overlap correctly. So let's say they have to be at least 1/4 of 1500. So that would be around, let's say, 325. Okay, that would be around 1/4. And let's compute. Okay, this was the input sound, the magnitude and phase spectrogram, and the output reconstructed. So let's first just listen to the reconstruction. Okay, that's pretty good. So I guess we haven't lost any information from the analysis. So that means that the hop size and the window size were chosen correctly, so that they overlap correctly. And well, in the phase spectrum we see it looks like very minimalist, but it's quite interesting. We see these very clear vertical lines, and these correspond to the attacks. Basically, this means that during these attacks, the phase is quite disrupted, is quite changed. There is a quite big transition there. And that's something that we see very clearly in the phase information. And in the more steady, during the notes, we see more this horizontal structure. That means that the harmonics maintain a kind of a phase continuity that can be identified in the phase spectrogram. In the magnitude spectrogram, we see we see very clearly the harmonics, these red lines, and we see that as the sound evolves, piano being a percussive instrument, in the attack there is more energy, and so there is more harmonics, and as the time evolves, the harmonics are decaying, and especially they decay the high harmonics, and the low harmonics are staying more. We also see quite clearly the attacks of the sounds and what is going on during the attack. So that's quite interesting. Okay, now let's zoom in And let's go into some detail of that. So let's use the option of this figure of doing zooming into a rectangle. And let's just take this middle node, the fourth node, from a little bit before the attack to around when the node ends. Okay, and that's what we're getting, and what we are seeing, in fact, is the discretization of the analysis. We have zoomed enough so that we can see this vertical kind of quantization, these vertical bars. These correspond to every frame, every spectrum computed. So at every bar correspond to the number of samples of the hop size. So this was these 325 samples that we are hopping from one frame to the next. And vertically, we also see this kind of discretization, these horizontal lines that are more narrower, because we have taken quite a bit of samples in the FFT. We have taken 2,048 samples, so we have a pretty good frequency resolution. Let's compute with a different set of parameters. For example, let's use a window size which is smaller. For example, let's use 201 samples, and let's use an FFT size correspondingly smaller. It doesn't have to be that big, so let's say 256. And of course the hop size has to be accordingly to the window size, at least 1/4, so let's use 50. And now let's compute it. Okay, it takes a little bit because it's of course, being the hop size smaller, it has to compute more FFTs. And this is the what we get. Basically, we are visualizing a similar thing, the analysis and then the resynthesis. And the synthesis is going to be pretty good. Let's listen to that. Since we have maintained the same relationship between the hop size and the window size, the identity is preserved. So the output sound is identical to the original. But now let's zoom into the same region that we zoomed before to try to understand the differences. Let's get a little bit before the attack, and let's get a little bit of the steady state. Okay, and let's compare it with the previous one. Okay, this was the previous, and this is this one. Well, quite different. If we mention what we were talking about before, the concept of the vertical and horizontal lines, in terms of the vertical lines, we see them narrower. There are more frames per second here. So the resolution, the time resolution, is bigger. Okay, so we see more things in terms of how things evolve in time. In exchange, at the vertical axis, the frequency resolution is worse because the FFT size was much smaller. Therefore, these boxes are kind of larger in the vertical axis. So we see less information in the frequency resolution domain. And this is at the core of one of the things that are fundamental for the short time Fourier transform, is what we call the time frequency compromise. In the first case, we had a good frequency resolution and a not so good time resolution. In exchange, in this second example, we have a pretty good time resolution but not so good frequency resolution. And that's a quite important consideration to take into account when we analyze a sound and to decide what is the best set of parameters for a particular sound. Okay, now let's go into one aspect, to the attack, and try to understand some aspect of the sound by looking at this fine spectrum analysis that we have started to do. So let's do the DFT. Okay, and we will just compute the DFT of one location at the attack. Okay, at the attack, more or less, it was around, let's see, it was 1.54. That's kind of where the attack is. And let's keep this same resolution that we have. So let's keep the 1501, and let's have the FFT size 2048, and let's use the piano sound. Okay, now we will compute it. Okay, this is the beginning, and we see here that is the attack of the piano. So we see quite a bit of things going on here, the phase and the reconstruction. Let's zoom into the beginning. So let's just get the magnitude spectrogram up to, let's say, well, let's get up to 10,000 hertz. Okay, so we see quite a bit of things. Let's now recompute this with the same parameters, but a little bit beyond the attack. So when more is a steady state. So let's say 100 milliseconds after. So 1 second and 64 with the same parameters. Okay, and this is another analysis. And let's again zoom into the same region. Let's just zoom into the region that goes until 10,000 hertz, and that we get all the information. Okay, and let's compare it, and let's see if we can understand what is going on at the sound level. Okay, this was the top is the attack, the bottom is the more steady state. In the time domain, clearly we see the difference. In the frequency domain, I believe we can see also significantly difference. For example, in the attack, the harmonics are not so well defined because it's the beginning of the sound. The harmonics have not been started completely. Instead, in the steady state, these peaks are much more clear, much more resolved. Okay. Then another thing is that in the attack, the kind of the noise floor, or basically the energy of the high frequencies, is higher. So the high frequencies are much louder than, or at least substantially louder than during the steady state, in which are the lower harmonics that are clearly louder. Okay, so this is a good way to try to understand a particular sound, a particular fragment of a sound, and do some analysis using the short time Fourier transform that gives us some insight into the sound. Okay, so that's basically all I wanted to say. So we have been looking at the sound, in this case the piano sound, using the SMS tools, and of course this sound is available under Freesound. And hopefully this has given you another insight into the tool we are building, in this case the short time Fourier transform, but at the same time has given you some insight into the piano sounds. And I believe it's quite an interesting instrument and sound, and using these tools we can appreciate quite a bit of it. So anyway, so that's it for the demonstrations of this week. So I hope to see you in next class. Thank you.